Today we are going to discuss few more sections of the chapter 2. We are going to learn about the forces, Newton's three laws of motion, and conservation of momentum. Please complete the lab 9 and 10 and their pre-labs, and also complete the homework number 3. In the previous section, we described the motion. We described the motion in terms of the distance, velocity, acceleration, time. All these variables we used to describe the motion was related to the kinematics. Then today we are going to talk about the dynamic. Then we want to describe the motion, but also we want to take into account the causes that produce that motion. That the cause that produces that any motion is force, is a force. Then we know we can think about the force when we push something, when we pull something, or when we kick something. Then what happens when we push something? We change the motion of some object. Yes, when we push the door, when we pull the door, we move the door. Then we change the motion. The door was at rest or was not moving, and then the doors was start moving. Then always the force is related to some change in the motion of an object. When we apply some force, we change the motion of the object. Then what happens if we apply force to some object? Then if the object is at rest, then it start moving. Yes, if the object is at rest and we apply some force, then the object start moving. Then when the object is moving, if we consider the initial velocity of the object is 0 and afterwards moving, then the final velocity of the object is not 0. Then there is change in velocity. When there is change in velocity, then we had some acceleration. Then always, if we apply some force to any object, then we can change the velocity of the object from 0 velocity to non-zero velocity. Means we accelerate the object. Also, if the object is already moving, a force is required to change the magnitude of the direction of the velocity. Means if the object is already moving, then a force is needed to stop the object or to change the direction of the object. And with all this, always when we are talking about change in the velocity, either magnitude or direction, means is related to the acceleration. Then in other words, to accelerate an object, a force is required. Because when we apply the force in different directions, we have different effects. And this is why the force is a vector. Then because force is a vector, both magnitude and direction are involved when we are talking about the force. Then because force is a vector, then we need to add the forces. We need to add that forces in the way we add vectors. Then remember, when we had parallel or anti-parallel vectors, we can add them as they were algebraic expressions. Then this is why in this case, because if we had parallel or anti-parallel forces, then we can do the same thing. If these two forces are in the same direction, both are, the direction is east, then what we can do to get the resultant force or the net force is the same thing. Just we add the magnitude, and the direction of the vector of the force will be east, the same direction. Then we add will be 2000 units in its direction. If we had antiparallel vectors, in this case forces, but they are in opposite direction, they are antiparallel, then the net force equals to 0. In the other case, if we had antiparallel forces that are not equal in magnitude, then what we can do is we will subtract the small number, the small magnitude, from the larger magnitude, and we will keep the force for the largest vector, or largest force in this case. And we subtract 2000 minus 1000 is 1000, because the vector in west direction is the largest vector, then the vector of the resultant, the direction of the resultant force is west. And in this case, the resultant force, or the net force, will be 1000 units in west direction. Now we want to talk about the kind of force, the types of force. There are two main types of force, which are contact forces and field forces. The contact forces results from the physical contact between two objects. Then in these forces the example for contact forces can be pull, push, kick. All these are examples of contact forces. Field forces, they act through the empty space. No physical contact is required. Then the examples for the field forces are gravitational force, electromagnetic force, nuclear force, and weak force. And in this chapter, we are going to discuss the gravitational force, and in the next chapter, we will take care of the electromagnetic forces, nuclear forces, which is developed in the nucleus of the atom, and weak forces is present in radioactive decay. Then we will take care of the gravitational force in this chapter. Then let's start with the three laws of motion. Then the law of motion, which was developed by Isaac Newton, explained the relation between force and motion. Then Newton also, he invented the calculus, he developed the law of motion and developed the law of gravitational attraction. And in this chapter, we will discuss the law of motion, and we will talking about the gravitational force. The Newton first law explained that every object at rest will remain at rest, or if it's moving, will be moving at constant velocity if there is no force acting on the object, or if the net force equals to 0. And basically, the first Newton law explains what happens if the net force acting on an object is 0. If there is no force acting on an object, or the net force is equals to 0, then there is two possibilities. The object is at rest, or the object is moving at constant velocity. Also, this law is called the law of inertia, because all the objects tend to remain either at rest or step-like motion. Yes, if there is no force that acting on the object. This tendency to resist the change in motion is known as inertia. And remember, we use mass is used to measure the amount of inertia of an object. More mass, more inertia. Yes, if we had some object with big mass, then to start moving that object it required more force. Yes, then that object, the tendency of that object is to stay at rest. Yes, if there is no enough force to move that object. Then in the Newton's second law, explain is what happens if there is a force that acting on an object. As this is that law explain. Yes, in the first explain what happens if there is no force, but here is in the second Newton law explain what happens if there is a force acting on an object. And before to discuss this one, let's review this concept. Inertia. Remember, inertia is the tendency of an object to stay at rest or continue in its state of motion if there is no force that acting on an object, or the net force equal to 0. And this is why the mass is a measure of the resistance of an object to change in its motion. Then this is why we can say the mass is the measure of inertia of an object. And this is why if we had some like here it is in this wagon, we had some blocks here, and if the wagon is moving, but here if the wagon is stopped, the blocks, they will move to the front because they will try to continue with the motion. Yes? They try to continue moving to front. And this is due to the inertia. Then let's now discuss the Newton's second law. This force, this law correlate three different quantities: force, mass, and acceleration. Then let's now think here we had an engine, we had some mass, that engine is moving. Then let's think the engines represent the force, and these wagons represent the mass. Yes, mass. Then what happened here is we will change the force, but we will keep the mass constant, and we will see what happened with the acceleration. Then what happens if we increase the force? What happens with the acceleration? More force, if we apply more force, then the acceleration is going to increase. Yes, more force, more acceleration. Then what we can say the force is direct proportionally to the acceleration if the mass is constant. Then the acceleration, more force, more acceleration. Then acceleration is direct proportionally to the net force if the mass is constant. Then let's now change the variables. Let's now increase the mass, but we keep the force constant. Remember, the force is represented by the engines. Then in this case, we had the force constant and we increase the mass. Then what happened with the acceleration if we increase the mass? If we keep the force constant, what happened with the acceleration? Then more mass, less acceleration. It's more difficult to move if we had the same force. If we keep the force constant, but we increase the mass, it will be more difficult to move, to accelerate. Yes, then more mass, less acceleration. Then more mass, less acceleration means inverse proportional. And this is why the acceleration and the mass, they are inversely proportional if the force is constant. Yes, and more mass, less acceleration. Now, if we combine these two results, we know more force, more acceleration, more mass, less acceleration. If we combine these two results, we will have the acceleration. Yes, acceleration is equal to the force, but the acceleration is inversely proportional to the mass. Yes, if we combine these two, we will have this equation. Acceleration is direct proportional to the force, but acceleration is inversely proportional to the mass. If we multiply by mass on both sides, we have this equation like that here. Net force, we multiply by the mass on both sides, this cancel out, the net force, or we can write this one, mass times acceleration. Yes. And this is usually the equation that represents the Newton's second law. Yes. This is usually the equation represent that is the same that we had here. Yes, just we wrote the equation in different way. Then the second Newton law say the acceleration of an object is direct proportionally to the net force, but is inversely proportional to the mass. Then here in this example, this person is riding the bicycle. Then that person is applying some force. And that person is moving with some acceleration. But what happens if now another person is in the bicycle? Then now we can think now the mass is the double. But we keep the force constant. We keep the same force, because you can see that second person is not pedaling. Then we keep the same force, but we increase the mass. Then what is going to happen with the acceleration if we duplicate the mass and we keep the force constant? Then if we duplicate the mass, the acceleration is going to reduce in half. Yes, the acceleration is going to reduce in half. Remember, yes, if we increase, this is constant. If we duplicate the mass, the acceleration, because they are inverse relation, is going to reduce in half. Let's now discuss the units of the force. And we will discuss in SI system and in English system. Then to know the units, we will use the equation. Now we know we can define the force. Force equals mass times acceleration. And here is the net force. And let's start with the units. This is why we had here these brackets. What are the units for mass in SI system? It's kilograms. What are the units for acceleration? Is meters per second squared. Then the units of force is kilograms meters per second squared. Then this units had special name is Newton. Then 1 Newton is 1 kilogram per meter per second squared. And we can represent by the letter N, as this is the Newton. Then 1 Newton is the force needed to accelerate 1 kilogram of mass at the rate of 1 meter per second squared in the direction of the applied force. Then 1 Newton is the force needed to accelerate 1 kilogram of mass at 1 meter per second squared. And the other unit for force is the unit in English system. Then we had here mass. The units for mass in English system is slug. The units for acceleration is feet per second squared. Then this combination has a special name is the pound force. It's pound force, and the symbol is this one. In your book, they use just this one. Use just pounds. But is the problem with this is what we can confuse this one with the units of mass. Yes. Then this is why it's good to use with one F here to indicate this correspond to units of force. Then in SI system, the units for force is Newton, and in English system, the units for force is pounds force. Now let's try to solve some simple problems just to try to understand the equation, the units. Then in this example, we had a 60 kilograms bicycle and rider accelerate at 0.5 meters per second square. How much extra force was applied? Then in this case, we had here there is then the mass of the bicycle plus rider will be 60 kilograms. And the acceleration, as this is moving, and the acceleration is 0.5 meters per second square. And we want to know what is the force was applied to this bicycle. Yes? Then we need to know what is the force. And we know by the second Newton law, the force is mass times acceleration. The force mass will be 60 kilograms times 0.5 meters per second square. And if we multiply 60 times 0.5 will be 30. And we have the units. Yes, don't forget to write the units. Then we know kilograms meters per second square correspond to Newton. Then we have here 30 Newton and one significant digit. Yes, we had one significant digit. Don't forget Newton equals to kilogram meters per second square, 1 Newton. And the force applied to the bicycle plus the rider is 30 newtons. And let's try now one more problem. Then we want to know in this case what is the acceleration of 20 kilograms cart if the net force on it is 40 newton. And in this case we have the cart, it's like some toy, yes. Cart. This car is moving with some force equals to 40 newtons, and the mass of the cart is 20 kilograms. And we want to know what is the acceleration. Yes. And let's write here the information we had here is 40 newtons, mass is 20 kilograms. We want to know the acceleration. One thing we need to always check if the units are consistent. Then you have to remember Newton is kilograms meters per second square. Yes. Then you need to check if the units of mass is also in kilograms. Yes, because we need consistent units. Otherwise, we cannot divide, multiply these numbers if they don't have the same units or the same kind of units. And here we had kilograms meters per second square. Here we had 20 kilograms. We had the same units, no problem. Then now we need to solve for acceleration. The force equals mass times acceleration, and we divide by the mass because we want to solve for acceleration. Then force let me write the other way. You can write this one, acceleration equals to force over mass. The acceleration equals to force. Force is mass is 20 kilograms. Now here is important we write the definition of the Newton. Then we can see here these kilograms cancel out, and the units of the answer is meters per second square, which are the units we expected because it's acceleration. Yes. And here will be 2.0 meters per second square, which are the units, and these are the units we expected because it's acceleration. In this example, we are going to apply equations that we learned before, which are the kinematic equation, but also we are going to apply the second Newton law equation, means the dynamic equation. And in this case, we had a car that is moving, but we want to know what force was applied in order to the car in order to stop the car. Then let's read the problem and try to understand. Then here is what average net force is required to bring a 1,500 kilograms car to rest from a speed of 28 meters per second. And in this case, we had a car that is moving at 28 meters per second. And we can call this one initial velocity. Then we want to know what force we need to apply in order to stop this car, yes, within 55 meters. Means if the final velocity equals 0. If we know the mass of the car is 1,500 kilograms. And let's write here, we know the mass of the car is 15 kilograms. The distance is 55 meters. The initial velocity is 28 meters per second. And the final velocity is 0. And we want to know what force we need to apply and what force we need to apply to stop the car. Yes, this is what we want to know. Probably let me do something here. Let me here right here. What force? And let's first review the equations we know. Then you will have this equation in your question sheet. I will send this one. Then force equals to mass times acceleration. Now, because the velocity changes, we know we need to apply the equations related to constant acceleration. And we will assume the car is moving at constant acceleration. Then this one is distance divided by time. This is one of the equations. The other is the definition of the acceleration. It's the change in velocity over time. This is, and the other one is the average. The other way we can calculate the average velocity. And finally, the equation that correlate the distance and the acceleration and time. As this is all the equations. Then to calculate the force, we need to know the mass. We already know the mass and the acceleration, but we don't know the acceleration. Then how can we calculate the acceleration? Then let's see with the information we had this equation to calculate the acceleration, but what happened is we need to know the time. We know the velocities, but we don't know the time. The other equation we can apply is this one, but again, we know the distance, but we don't know the time. Then we need to find first the time to get the acceleration. what is the other equation that correlates time? This one. But in this case, we know the distance, but we don't know the average velocity. And we need to find the average velocity to calculate the time. And we can calculate the average velocity using this equation. Then you can see here, to solve this problem, we need to solve multiple steps. Yes, we need to do multiple steps to find the acceleration. Then in this case, first what we will do, we will find the average velocity. Then we will apply this equation to calculate the time. Then if we know the time, now we can calculate the acceleration. And finally, we will calculate the force. Once you know the time here, you can use also this equation to calculate the acceleration. But it's a little more complicated. Then let's use the equation the equation with number 3. And let's start. Let's calculate first as the average velocity. And the average velocity equal to final will be 0 plus 28 meters per second divided by 2. And the average velocity is 14 meters per second. Then we're done with the first. Now we can calculate the time, yes, because this is why we are doing all these steps, because we need to calculate the time. And now let's calculate the time. Then to calculate the time, we need to solve for t first. And you can solve in the way you want. Probably here it would be easier. We multiply and cross multiply. Then now we need to solve for the time. Then we divide by the average. And now we can calculate distance is 55 meters divided by the average velocity, which is 14 meters per second. Then the time in this case will be, we need two significant digits. If we divide this, will be 3.85. And you see we have meters, but here is divide. Yes, then we need to flip the units. This cancel out and the units is in second as we expected. Then let's write this one with two significant digits and the units. Then the time is 3.9 seconds. Then now we're done with this. We're done with this. Now we need to calculate the acceleration. And the acceleration equals to final divided by the time. Final is 0 minus 28 meters per second divided by the time, but the time is 3.9 seconds. The acceleration equals to negative, as negative, because we have here negative, and negative, in this negative indicate the direction of the acceleration, as the direction of the acceleration, 7.179, and we had meters per second. And remember, this is, we need to flip this fraction to this unit, and it's 1/2 second. And the acceleration, if we write with the right number of negative 7.2 meters per second squared, which are the unit we expected for acceleration. And finally, now we can calculate the force. Yes, force equals to mass times acceleration. Force equal mass is 1500 kilograms times negative 7.2 meters per second squared. And the force equals to 10,800 kilograms meters per second squared. if we write this one with the correct number of significant digits, we have 11,000. And we know kilograms meters per second squared correspond to Newton. Also, you can write this one like 1.1 10 to the power 4 newtons. This is 4. Then, and here, one thing I forgot was the negative. Yes, because we multiply by the negative. Again, with this negative, let me write here the negative also. The negative indicate the direction. See, the force is pointing to the negative direction. Yes. Let me write. Because force is equals to mass times acceleration, force is a vector, acceleration is a vector, then always force and acceleration, they have the same direction. Then force is pointing to the west, we can say, or to the negative direction of x, and acceleration is also point to the same direction. Because mass is a scalar quantity, mass doesn't have any direction. This is why if the acceleration is negative, the force is also negative. And this is the force needed to stop the car. This is negative 11,000 newtons. Here we had one more example. Remember, we say if the forces are anti-parallel, we can calculate the net force just if we subtract the small force from the larger force. And what happened is, in this case, we had this rider that is pedaling, is moving, and the force are applying on the system of bicycle plus rider are the resistance of the air, yes, is this force, is the friction force, is the friction between the wheels and the rod, and the other force is the force is applied by the rider, yes, to the bicycle, because it's moving. What happened is, if in this example, if we add these two forces, yes, these two forces are in the west direction, we can say, yes, and this one in the east direction. Then if we add these two forces and then we subtract to the applied force, we got that the net force equals 0. But still, even the net force equals 0, the bicycle is moving. Then why, if the resultant force is 0, or the net force equals 0, if the net force equals 0, we know the acceleration must be 0, because we know force equal mass times acceleration. The acceleration is not 0, yes? Then the only way we can get 0 on both sides is the acceleration is 0, yes? We can get through a statement. And if the force is 0, the acceleration must be 0. But why, if the force is 0, the net force is 0, the acceleration is 0, why still the bicycle is moving? How it is possible? Then the reason is, the only way the bicycle move is if the bicycle is moving at constant velocity. Remember, the only way that some object is moving and the acceleration is 0 is if the velocity is constant, if there is no change in velocity. Yes, then the acceleration is 0. Remember, the definition of the acceleration is change in velocity over time. If the velocity is constant, it's always the same. If there is no change in velocity, let me write here maybe. if there is no change in velocity, if the initial and final velocity, they are equal, then the acceleration is 0. And the only way the acceleration is 0 and still some object is moving if the velocity is constant value. Then remember, if some object is moving at constant velocity, then the acceleration equals to 0. Now we want to discuss one kind of force. Then what kind of forces is the weight, which is called also the force of gravity. Then we already defined the mass as is a measure of the resistance of an object to change in its motion due to a force. And we know the mass is a scalar quantity, and this is why the mass is the measure of inertia of an object. Now, if we know the general equation for any force, yes, that the second Newton law defines the general equation for any force. Then if we define the wave of the force due to the acceleration of gravity, yes, if we define the wave as the force due to the acceleration of gravity, and we use this equation to try to find the equation for weight. Then in this case, what is the force? Force is the weight. Mass is the mass of the object. This is why we just write mass. But in this case, the acceleration is the acceleration of gravity, which is 9.8 meters per second squared. And this is why the equation we can use to calculate the weight of the object, or the force due to the gravity, the force due to the acceleration of gravity, is just we multiply the mass times g. G is the acceleration of gravity. And because weight is a force, then the units for weight is the same units for any force. It's Newton in the SI system or pound force in the English system. And we can see is we got the definition of the wave using the general equation for force, using the second Newton law. One more thing, because force is a vector, weight is also a vector. Yes, it's a special kind of force. It's always the weight is always point downward. Yes, it's always the vector that represents the weight is always point downward. Now let's understand that mass and weight are two different quantities. They are not the same. Yes, we already defined mass. Yes, is a measure of inertia of an object. Also is the amount of matter that makes up an object. Then now we want to define weight. Yes, now we know a mass is scalar quantity. Now what happened with weight? Weight is a force. Yes, first is a force, and is the force due to the acceleration of gravity. Yes. Then again, now we know mass and weight are two different quantities. One, mass is a scalar, weight is a force. Yes, it's two different quantities. What happened is the mass is the same value for any location. It's always the same because it's intrinsic property of the material. For example, the mass of some object in our planet, in Earth, is 10 kilograms. The mass on the moon will be also 10 kilograms. However, the weight will be different because weight depends on the acceleration of gravity. Because the acceleration of gravity is not the same on Earth and on the moon, then this is why the weight is different. Then the weight of this object on Earth is 98 newtons, but the weight on the moon will be 16 newtons. then the mass is independent of the location. However, the wave depend or can be changed, can be varied with the location. Then again, mass and wave, they are different quantities. Then let's try this problem. Then we want to calculate what is the weight of a 60 kilogram person on the surface of Earth. Yes, then now we know weight equals to mass times g value. Then the mass will be 60 kilograms and the g value is 9.8 meters per second squared. G value is a constant value. Yes, it's always the same, at least in our planet. Then now we know the mass, we know the G value, then we can calculate the weight of this person. Yes, it's 60.0 kilograms times 9.8 meters per second squared. And the weight in this case will be 588 kilograms meters per second squared. We don't take into account the significant digits of the constant values, then this is why the weight in this case will be 588 kilograms meters per second squared is Newton, as we expected because we know weight is a force. Yes, this is why the units must be Newton. And you can see when we lift, this is, you will have idea about the Newton. If you want to lift 60 kilograms person, then the force you are applying is about 600 Newton. This is, you have idea how much force is 10 newtons or 600 newtons or 11,000 newtons. Yes. Let's try one more example in which we apply the concept of weight. We had in this example a 60 kilogram person weighs 100 newtons on the moon. Then we want to know what is the acceleration of gravity on the moon. And we know the mass of this person is 60.0 kilograms and the weight on the moon is 100 newtons. And we want to know what is the acceleration of gravity on the moon. And what we know is, we know this value will be now 9.8 because 9.8 is the acceleration of gravity on Earth. Then this should be another value, yes, less value compared with the acceleration of gravity on our planet. And this is the equation. But in this case, because it's the weight on the moon, then we will find the acceleration of gravity on the moon. We need to solve for the acceleration of gravity, then we divide by the mass on both sides. And we can write here the will be equal to the weight divided by the mass. Weight will be 100 newtons divided by 60 kilograms. And just here, I want to rewrite this one. 100 newtons, we can write this one like kilograms meters per second squared. And the other is 60 kilograms. This is the definition of Newton. And we can see the kilograms cancel out and the units are meters per second squared. These are the units we know. These are the units of acceleration. Then 100 divided by 60 will be 1.66 meters per second squared. Now, if we write this one with 3 significant digits, because we had 60.0 there, yes, then we can 1.67. Here I want to mention using Newton over kilograms. I will write here this one. These are units of acceleration. Yes, we are not really familiar with these units. We don't use much this. But this is the same as meters per second squared. Yes, both are units of acceleration. Then we mainly use these units. Yes, we use in this course we will use mainly this unit. But Newton over kilograms are also units for acceleration, which is the acceleration. Here we had an acceleration, yes, acceleration of gravity. Then the acceleration of gravity on the moon is 1.67 meters per second squared. Now we are going to talk about the Newton's third law, and this Newton explains what does happen if two objects interact. And when two objects interact, one object exerts force on the other object, and also the other object will exert force on the first object. But these forces are equal and in opposite direction. For example, in this case, the hammer exerts some force on the nail. Probably you can see this one here is the nail. But at the same time, the nail exerts some force on the hammer. And this is why the hammer is moving back. Yes. Then these two forces are called action and reaction force, and always they come in pairs. And always when two objects interact, then will be action and reaction force involved. For example, if we push the table, then we are exerting, or our hand is exerts some force on the table, but at the same time the table is exerting some force on the hand. Then what happened with these two forces? The first, again, I want to repeat, these two forces are they had the same magnitude, but they had opposite direction. Then one force is the action and the other force is reaction. Doesn't matter what is the action and reaction force, yes, but one is action, the other is reaction. And one important thing is the action and reaction force always act on different objects. We can see the second Newton law. Yes, this is, we have force equal mass times acceleration. That net force is all the forces acting on one object. Yes, is acting on one object. But the action and reaction force, that forces are acting on different objects. And one example of the action and reaction force is why the ball bounces. When the ball hit the ground, the ball exerts some force on the ground. At the same time, the ground exerts the same force but in opposite direction to the ball, and this is why the ball bounces off. And also this is why we can walk. Yes, when we walk, we exert some force on the ground, but at the same time, the ground exerts some force on our foot, and this is why we can walk. And also here, this example is in your book. Yes, if in this case is the astronaut exerts some force on the satellite, then at the same time the satellite will exert some force on the astronaut. And again, action and reaction force always come in pairs, and they have the same magnitude but opposite direction. Then here we can summarize the Newton's third law that explains what happens with two objects interact. And always, if two objects interact, then will be action and reaction for present. Yes? These forces are equal in magnitude, but they act on different directions. In this example, we are going to apply the concept of the third Newton law, the second Newton law, and some kinematic equations. And in this case, we had an astronaut. The mass of this astronaut is 60 kilograms, and the mass of the satellite is 120 kilograms. Then, according to the example, this astronaut exerts a force of 30 newtons on the satellite for 1.50 seconds. Then we need to calculate, or we want to compare the forces that the astronaut exerts on the satellite and the satellite exerts on the astronaut. Also, we want to calculate the accelerations for both, for the astronaut and for the spacecraft. And we want also to calculate what is the speed for the astronaut and the satellite after they were in contact and they moved to the original positions. Then let's try it with the first one. And in this case, we had, let's solve the number 8. And in this case, we had the astronaut, and here we had the satellite. And according to the problem, the astronaut exerts some force on the satellite. Yes. This is the force. Let's say this is 1, this is 2. Then is the force that 1 exerts on 2. Yes. And we know this force is 30 Newton. Yes, is the force is feeling is the force exerted on the satellite. Then we know this force. Let me write here the force 1, 2 equals to 30 newtons. But according to the third Newton law, if these two systems they are in contact, then we can apply the third Newton law. Then the satellite will exert some force on the astronaut that will be the same magnitude but the opposite direction. And we can say this is the force to apply on 1. This is the force. And this force will be the same magnitude but opposite direction. And in this case, we know, according to these two forces are, and probably we can write here the negative. Yes, and these two forces are the same magnitude but opposite direction. And let's try now to solve the part B of the problem. In the part B of the problem, we had two systems, or we had two systems. One is the astronaut and the other is the satellite. And let's write, because now we need to be careful. We had two masses, then we want to identify each of this information. In this way, we don't get confused. And this is number 1. And then number 2 is the satellite of the spacecraft. Then first we know the mass. 1 is the astronaut is the 60 kilograms, but the second mass is 120 kilograms. We know the force exerted on the astronaut was negative 30 newtons. Negative 30 newtons. And the other force that was exerted on the spacecraft was 30 newtons. And we know, and I will do that part here, we know according to the second Newton law, the force equals mass times acceleration. Then if we need to solve for acceleration, because we want to calculate the acceleration, astronaut and the acceleration for the spacecraft. Then we divide by the mass, and we will have the acceleration equals to force divided by the mass. Then we can apply this equation to calculate the acceleration. Then will be force will be divided by, then this acceleration will be negative 30 newtons divided by 16.0 kilograms. Then this acceleration will be negative, because it's negative 0.5, and just write the three significant digits. We know Newton over kilograms is meters per second squared, as we discussed in the previous example, this relation. And we had the acceleration for the astronaut, and now let's calculate the acceleration for a spacecraft. Then we will have here 2.1 divided by, in this case will be 30 Newton divided by the acceleration of the spacecraft will be 0.250 meters per second squared. Then we can see the force that was exerted on the astronaut is in negative direction, and this is why the acceleration is also negative, because we know by the second Newton law, force and acceleration, which are vectors, they always point to the same direction. Now let's try the last problem. Then, and let me write here I will write some of the information we already know. We call this one 1. Here we have the space graph, which is number 2. Then what we know is the acceleration for the astronaut was negative 0.500 meters per second squared. And we know the acceleration 0.25 meters per second squared. And what other thing we know, yes, is the time the force was exerted was for 1.50 seconds. Then we want to write here this time, and the time is the same for both, yes, 1.50 seconds, the same time. Then if we assume the initial velocities for both the initial velocities for those were equal to 0, then we'll write here and now we want to calculate the final velocity for the astronaut, and we want to calculate the final velocity for the spacecraft. I need to write here 2 because we had 2 final velocities, now to identify each of these final velocities. And to do that, if we know the acceleration and we know the time and we know the initial velocity, then we can calculate the final velocity using the equation that define the acceleration. As the acceleration, probably I will write here the time, but we know the initial velocity equals to 0. Then finally we have the acceleration equals to the final velocity divided by the time. But we need to calculate the final velocity, then we multiply by the time on both sides. And the final velocity is just the acceleration multiplied by the time. And let's apply this equation to calculate the final velocity. Acceleration is In this case will be acceleration 1 multiplied by the time negative 0.500 meters per second squared multiplied by 1.50 seconds. Then the final velocity in case of the astronaut will be negative 0.700 with 3 significant digits meters per second. This cancel out with this. Yes, meters per second is velocity. Now let's calculate the final velocity for the spacecraft. Then will be, in this case, will be the acceleration is 0.250 meters per second squared multiplied by the time, seconds. We multiply these two numbers will be 0.365 meters. We expected meters per second because it's velocity. Then these seconds cancel out with one of this one. And finally we have meters per second. Then this is the velocity for the final velocity for the astronaut, and this is the final velocity for the spacecraft. And here is just the equation we use to solve the problem. Then the last thing we want to discuss today is the concept of momentum. The momentum is the product of the mass of an object and its velocity. And this is why momentum is just the mass multiplied by the velocity. Then the symbol to represent momentum is the lowercase p, and p equals to mass times v. The units for momentum are kilograms meters per second. There is no special name for this group of units. Then just the units for momentum will be kilograms meters per second in SI system. Then one of the important applications is the conservation of momentum, and this law says that the momentum just before the collision and after the collision are the same. And we can apply this one because during the collisions, the force that are present at that moment are really large compared with any other force. It's like when the collision occurs, that forces that appear in this moment, yes, are really large compared with the friction force, for example, with the air resistance force, with the weight, and it's like we are taking into account just the forces appear during the collision. And this is why we can apply this one to solve problems during collisions. Solving this problem using the kinematic equation or using the second Newton law are complicated because it's difficult to calculate that forces that appear in just small time, yes, in just a fraction of seconds. And this is why we can use the conservation of momentum to solve this kind of problem. And this is what we are going to do now. Then if we apply the conservation of momentum, we say if this is just happened before the collision. Yes, this is here we have the masses and the velocities just before the collision. And this is when the collision occurred, and this is the situation just after the collision. And if we calculate the momentum in this point and the momentum in this point, these two momentums must be equal. We need to calculate the total momentum, means the momentum for all the objects involved during the collision. And in this case, the momentum for the truck will be the mass of the truck multiplied by the velocity of the truck. The momentum for the car will be the mass of the car multiplied by the velocity of the car just before. And we had to do the same after the collision. The mass multiplied by the velocities in this. And if we can consider the external force almost absence, if we consider there is no external force, then these two quantities must be equal. And in this case, if we calculate the momentum before, we have the mass of the truck multiplied by the velocity will be 1,000. Let's try to apply this equation to the numbers we have there, and will be 1,000 kilograms. Yes, this is this one. The velocity will be 5 times 5.0 meters per second, plus the momentum of the car will be 800 kilograms multiplied by 2.0 meters per second. Then this must be equal to 1,000 kilograms is the mass of the truck. Now we are the other side of the equation, times 3.4 meters per second, plus, I will write the second part here, this part, because I don't have enough space here, will be 800 kilograms times 4.0 meters per second. If we multiply these two numbers together, we have 5,000 kilograms meters per second plus 1,600 kilograms meters per second. On this side, we have 3,400 kilograms meters per second plus 3,200 kilograms meters per second. If we add this, we can add because we have the same units. Yes, then we have 6,600 kilograms meters per second, and we have the same on the other side. Yes, it's 6,600 kilograms meters per second. And in this particular case, we can apply the conservation of momentum. The momentum before and after are the same. And we can apply this one because what happens during the collision is the momentum that is lost by one object is gained by the other object. And this is why at the end the total momentum is the same, it's constant. Yes? And the momentum that is lost by the truck is gained by the car. Yes, is lost by the truck. In this case, it's lost by the truck, but then it's gained by the car. This is why when we add the momentums just before and after, we had the same value. We had constant value. Then now in this example, we want to bring the result we got for the astronaut and the satellite problem, and we want to apply the conservation of momentum to this problem. Then what we will assume is we had to assume is the momentum just before and after the interaction was the same. Yes, this is we will assume, and we will try to see if this is true for this example also. And in what happens in this case, this is the situation. Here is the then this is before the interaction. Yes, here we don't say collision, is the interaction in this case. And here is where the interaction happened. and this is just before, so just after the interaction. And here they was the initial velocity in this is 1, this is 2. The initial velocity for 1 was right here. The initial velocity for the satellite was 0, but here they move, and we found this one as the final velocity was negative point, but the final velocity for the satellite was 0.0 meters per second. And if we want to apply the conservation of momentum, we need to apply the momentum just before and after the interaction. And then we will see if the momentum before and after they are equal. Then let's write the complete equation. And here is the equation. We need to add the momentums for the astronaut, for the satellite, which are 1 and 2, but just before. And then according to the conservation of momentum, this must be equal to we add the momentums after the collision. Let me write here after the collision, so after the interaction, these two must be equal. Then what happened is, this was the initial, here these are we call the initial velocities in this case, these velocities. And what happened if we multiply any mass, that we know the mass is 60 and 120, by 0? What happened if we multiply 120 by 0? We know these velocities just before the interaction, that velocities were equals to 0. And we know this velocity equals 0, this velocity equals 0. Yes. If we multiply any number by 0, we will get 0 here. Yeah. Then we will have this. And let's now see if in this case we can apply the conservation of momentum. We know this side equals 0, and the other side, if the momentum is constant, then the other side must be equal to 0. And we can test that. We can try. Yes, we had 0 here. Now we know the mass for 1. This is, in our case, this is 1. This is 2. In our case, the mass 1 will be 60 kilograms. The velocity, this is, in our case, this is this velocity. We call the final velocity. Negative, let me write here the negative. This corresponds to the negative 0.0 meters per second, plus mass 2 will be, the mass of the spacecraft will be 120 kilograms, multiplied by the velocity after the collision, which is 0.375 meters per second. And if we multiply these two numbers together, we will get here negative 45 kilograms meters per second, plus if we multiply these two numbers, we will get, let me write the correct number of significant digits, will be negative 45.0. Negative 45.0 kilograms meters per second. We had negative 45 kilograms meters per second, plus 45 kilograms meters per second, and we know this equals 0. And we can see we can apply the conservation of momentum in this situation. One more thing I want to show here, and I want to bring this equation if the total momentum of the system equals 0, that is before or after, if the total momentum of the system is 0 before or after, then we will have this equation, yes? And then we can write this one like, if we subtract on both sides the same term, then we will have this one, and we will have here negative equals to this one, as we will bring this one down with that. And this is the equation is in your book. But again, this equation is not with the negative, but I think the negative is important because it's telling the velocity, the velocities are in opposite direction. Yes? When there is interaction, the velocities will be in opposite direction. Then this is the equation is in your book, but this equation works only if the total momentum equals 0 before or after the collision, like in this case. Then this is why always I prefer to start with the original equation, with this one. Yes, and this is the I suggest you to do it, because in some cases, in some problems, the momentum is the total momentum before or the total momentum after is not equal to 0. And now let's see, we had this problem. We had the rifle and bullet problem. And in this case, we had a 4 kilograms rifle, fires a 5 10 to the power minus 3 kilograms bullet at a velocity of 500 meters per second. Then we want to know what is the velocity acquired by the rifle. Then we want to know the recoil velocity, as this is we want to calculate. And after shooting, we want to calculate the recoil velocity of the rifle. Then this is the situation we had. Then this is happened before shooting. This during shooting, but after shooting, this is just after shooting. What happened is the velocity of the bullet is this one, but we want to know what is the recoil velocity of the rifle. And we want to start with this equation. We can say 1 is for the rifle. Yes, we can say 1 is for the rifle and 2 is for the bullet. Here is the bullet 2. Unless maybe we can write here. This is rifle, and we have bullet here. This is 1. This is 2. Then we know the mass for the rifle is 4.0 kilograms, and the mass for the bullet is 5.0 10 to the power minus 3 kilograms. Then what happened before the collision is everything is at rest. Then the velocity for 1 equals 0 and the velocity for 2 equals 0. This happened before the collision. But what happened after the collision? Then what happened with the velocity of the bullet? We know the velocity of the bullet is 500 meters per second. but we don't know this one. This is the velocity we want to calculate, and this happened after. And we had this situation, we had this information. Now let's try to start with the conservation of momentum equation. Then before, these two velocities are zero. Yes, these two velocities are zero. Then this is zero, this is zero. And if we multiply any number by zero, we will get zero. And we had zero on this side, and then we had this. Now we need to solve, in this case, we need to solve for B1. This is the velocity of the rifle after the shooting, after shooting, after we call the collision. Yes, we are saying the collision. Then we need to solve for this variable. Then first we need to subtract this on both sides. And again, in your book, you will see this equation, as this is the equation they suggest to use. Then we want to solve for, we divide by mass 1. This is the mass of the rifle, negative, because we want to solve for the velocity of the rifle. Then finally, we had the velocity of the rifle equals to negative. And you can see the bullet is moving towards positive direction. And we can see the rifle is moving toward negative direction. This is why the velocity of the rifle is negative. Yes, it makes sense. It's moving in this direction. Yes, this is why this velocity is negative. And now we can just calculate the mass of the bullet, which is 5.0 10 to the power minus 3 kilograms. Velocity of the bullet will be 500 meters per second, divided by the mass of the rifle, which is 4.0 kilograms. And if we divide all these quantities, then we will get, then we need to give with two significant digits, because here we had two significant digits in these numbers. Then we got point negative. Let me write the negative first. And wait, I need a little more space here. It will be negative 0.625, and we can see the kilograms cancel out, and the answer is in meters per second, which are the velocities, the units of velocity. And if we want to write with the correct number of significant digits, meters per second, which is the recoil velocity, and it's negative. Remember, this negative means indicate the direction of the velocity, and it's a small velocity. Yes, because it's when the recoil velocity is you move slowly back. Yes, this is why that velocity is small. It's negative 0.63. And this will be the last problem we are going to discuss today. And in this case, we will see the total momentum before or after are non-zero. And in this case, it's very important you had to apply the whole equation, this equation, to solve the problem. And let's see what we had here. In this case, we had a 20,000 kilograms railroad car, and it's costing 3 meters per second when it collides and couples with a second identical car at rest. Then what is the resulting speed of the combined cars? And this is the situation we had in this case. I will try to write better. So, this is the first card, that's right here, and this is the second card. Then according to the problem, the mass of these two cards are the same because they are identical cards. And we can write here, let me write here, mass 1, 20,000 kilograms, the mass 2, 20,000 kilograms. But what happened with the velocities before? Yes, this is happened before. What happened with the velocities? This car was moving. Yes, the velocity before, for one, was 3 meters per second. But the other car was at rest. Then this car equals to 0. And then the collision occurred, as this collides. And now what happened is, after the collision, the cars, they move together, as they move together. And these cars, they move together. And we want to know what is the speed of the combined cars. And we want to know what is the speed that both are moving. The speed of the system of the both cars. Then what happened with the velocities of this and the second car after the collision? Because they move together, they are moving at the same time, then we can say the velocity, these two velocities must be the same because they are moving together. But we don't know the velocity. This is why we use just v to indicate just one variable. Then in this case, we don't have two variables. We have just one. Yes, it's the velocity of the combined cars. And why? Because they are moving together. These two velocities are the same, and this happened after. Now we need to apply the equation to solve the problem. As you can see in this case, this term is not 0. Yes, this velocity is 0, but this velocity is non-zero. And this is why now we need to take into account the whole equation. Yes, we cannot apply this equation. Yes, that is in your book. Yes, we cannot apply just this equation. And in this case, let's try to write the equation here. Let me write here the equation. Let me write before. Must be equal to we add the momentums for both cars, but after the collision. And what happened now before? Let's now concentrate on this part. This velocity equals 0. And we say if the velocity is 0, this term is 0 also. Because if we multiply any number by 0, you will get 0. Then, but this term is non-zero, yes, because we had some velocity. There on this side, what we had is this one. Let's see what we had on the other side. Then these are non-zero, but we know these are the same. Yes, these two velocities are the same, and we can use v to identify both. And we can say this one is v because this equals to v. And this also is v because this equals to v. Now we need to solve for this variable. This is the variable we want to find. Then we need to solve for v. And to do that, what we can do, but we have v on both terms, then we can factor out. Yes, this is a common term. Then what we can do, we can bring this one from, we can factor out. This is like the opposite of this distributive property. If we multiply this v times n1, we will get this one. If we multiply velocity times mass 2, you will get this one. Then we factor out v. Yes, it's a common term. It's here, then we just pull this one in front. Because we want to solve for this, for v, then we can divide by this term. This cancel out, and finally we have the velocity of the combined cars will be, as you can see, this equation is different. Yes, it's different. Then now what we need to do is just replace the values and calculate the velocity. And let's write the values. Mass 1 is 20 kilograms. V1 is 3 meters per second. And these masses are the same. It's 20 kilograms plus, let me write, plus 20 kilograms. Then the velocity will be kilograms 3 meters per second divided by 40,000 kilograms. In this part you can skip some steps, but I want to do with all the steps. And if you can see kilograms cancel out and the units is meters per second. And here you will have the answer is 1.5 meters per second. And the velocity is 1. And I know if we round, if we take into account the significant digits will be 2, but I want to show or leave the answer like that because I want to show this one something. You see, because according to the conservation of momentum, the momentum lost by one car is gained by the other one. Yes. In this case, what happened is because the mass now is the double, yes, it's twice, the mass now is twice of the original mass. And what happened, the velocity is going to reduce by half. Yes, you see, here we had, in this case, we had 20 kilograms, but in this system, we had 40,000 kilograms. Then we had the double of the mass, we had twice of the mass. And what happened with the velocity? Velocity is going to reduce half. In this way, the momentums will be conserved, we had the same momentum. And this is why I want to leave this one with 2 significant digits. But this happens only if the masses of the objects are equal. Yes, if the masses are different, then we cannot do this analysis like that. Yes, but this is something. Now you know, if you had identical masses, then, for example, if the mass is 3 times, then the velocity is going to reduce by 3. Yes, and in this case, the mass is twice, then this is why the velocity is reduced by half. And this is all I had to discuss for today.